All right, this is my talk, The Functional Final Frontier. I'm David Nolen. I was formerly at the New York Times. I left the New York Times, actually, last Friday. I'd been there for 4 years as a front-end JavaScript developer. I now work for Cognitect. They are the sort of stewards of the Clojure programming language, as well as the Datomic database. I'm not going to talk about any of those things today. I'm going to talk a bit about what I call the Functional Final Frontier. And the reason this talk has a curious title is because I've been doing basically object-oriented user interface programming for 8 years now. And I'm kind of excited about taking the lessons I learned from OO approaches to user interfaces and combining with those approaches with the lessons from functional programming. User interface programming basically happened almost at the exact same time as object-oriented programming. This is an image of the Xerox Alto running a Smalltalk system. And these kids they're sort of like doing interactive computing, sort of something that you could recognize today for the very first time. And this was built with an object-oriented system called Smalltalk, developed by Alan Kay. If you can actually still fire up a Smalltalk image today. There's a really great open source Smalltalk called Squeak. I highly recommend it. What's fascinating is that in 35 years' time, I believe this is an image of Smalltalk 80, you will be able to identify most of the sort of elements of an object-oriented system that you would interact with today. It's not that different. In fact, if you went through the sort of what's called the system browser, which exposes all of the classes of the Smalltalk system, you would probably see things called models, views, and controllers, because that was also invented at Xerox PARC. It was first formulated by Trygve Rinskog, Adele Goldberg, and others at Xerox PARC in 1979. So 35 years, people are still building model view controller systems. So the concept has a very long shadow. Ideas still very prevalent today, and I would say that's because good ideas tend to eat their children, and so I think if we're going to move beyond MVC, I think we have to come up with something significantly better. So I do think that at a very abstract level, I think there's, MVC is sort of a sound separation of logical concerns. In the end, though, I think the part that I'm moving away from personally, and I'm trying to sort of speak about why I think we should abandon some things, is that the implementations leave a lot to be desired, because most people, when they build MVC systems, they are constructed on stateful objects. And of course, if you've done any OO, you're like, well, of course it has to be done with stateful objects. How is it possible to design UIs without stateful objects? And that's what my talk is about today. It is actually possible to design object-oriented systems without stateful objects everywhere. But to sort of throw a wrench in that entire narrative of the sort of the history of the user interface, here we have an image of a Next machine with the very first web browser. This was built by Berners-Lee using a very rich, powerful, object-oriented framework, which eventually became Cocoa. And it's the same logical framework that runs on your phone, right? Same architecture. So this was what, 87? No. Oh, I forget the year that this came out, but a very long time ago. And then fast forward to today, and who would have imagined that the primary mode of interaction for most people on their computer is via the web. Apps have come along, and of course, apps play a big role. But to a large degree, most of our interactions happen online, and many of them happen through the web. Now, the problem is that when Berners-Lee created the first web browser, the intention was never for the web browser to be a rich interface, right? It was like hyperlinks and text, and it was document-oriented. And that made sense because there was already extremely powerful desktop GUI systems, like I said, like Next, Step, which eventually became Cocoa. So the document object model really was never designed to solve the same kinds of problems. Yet, here we are today attempting to build rich interactions inside of web browsers. And so you have this issue, right? The document object model doesn't actually map to user interface widgets or the typical types of things you want to do in user interfaces. So you basically have JavaScript, which was, again, a language not designed for experts, on top of a mutable DOM, which was never intended to do serious user interface programming, on top of what I would say are sort of like best attempts at doing MVC systems. But again, I think they're sort of built on top of a stateful paradigm, which I think is eventually going to be a dead end. And basically, who here does any JavaScript programming or has done like, okay, good, great. So a lot of you, so a good number of you. So after having done serious JavaScript programming on the web, building user interfaces for 8 years, I mean, you get to this point where you really feel like Alan Kay has this great analogy about software architecture, that most software architecture looks like the Great Pyramids, right? It's very impressive, but there's no big idea here. There's no serious concept at play. It's that brute force, hundreds of years, thousands of people, right? So that's really what modern software architecture is like in many cases. And he has this really great analogy where he says, I mean, all architecture really needed was just a very simple, a truly simple, profound concept, and you could have a radically different architecture. Sort of like you would be able to more efficiently distribute the sort of the architectural materials. And in this case, he's pointing out the arch, right? Once we understood the arch and the architectural implications of it, we were able to build entirely different types of things. So what is, part of me feels like when I'm doing user interface programming, what's the arch? Like what's the concept that I still think that we haven't found today? So we know what objects have to offer, and actually objects have a lot to offer, but I don't think it provides the arch. But what about functional programming? I'm a big fan of functional programming, and so what is functional programming offering in this space of user interface, the design of user interfaces? So there's a great thing called functional reactive programming, FRP for short. It's still an active area of research if you're talking about the pure form of it. It arose out of Haskell. It's really amazing stuff. Probably the coolest implementation I've seen is Elm, who's actually, I believe Evan will be talking about either, I think, today or tomorrow, but you should check it out. Elm is very cool, and in fact, it does a lot of the things that I'll be talking about today. There's also RX. Microsoft has this thing, reactive extensions. There's reactive Cocoa, reactive Java. These things are interesting, but the problem with reactive extensions is it's really a coordination language, and it doesn't really talk too much about the endpoints. Like, how do I render something in a functional manner? There's another thing called communicating sequential processes, and that's like if you're a fan of Go, the Golang, they use CSP. Clojure, which is a lot of what I'll be talking about today, also has something called core async, which is also a form of CSP. But again, it's a coordination language. It's doesn't really address the fundamental problem. How do we efficiently render something? How do we render something when the target at the end is something mutable, like the DOM? So you might get to this point where like, wow, 35 years of object-oriented programming, 56 years of functional programming, and there doesn't seem to be a solution. Maybe there isn't an arch. And I would actually say, if you're from the functional programming community, you would know this a little bit better, but there is actually a pretty awesome idea here that I think serves the purpose. And that's what's called purely functional data structures. So in 1997, this guy, Chris Okazaki, said, not a lot of thought has been, sort of a survey has been done, like how can you do immutable functional data structures and get good performance, like good complexity. And so he collected some of this work, and thanks to Phil Bagwell, who passed away, who was at EPFL, and he wrote a lot about this thing called the hash array maps try, and then Rich Hickey, who invented Clojure, came along and created an immutable variant, and that sort of kicked off a wave of research across many functional programming languages on doing higher performance immutable data structures. So Clojure ships with a bunch of these, and actually Clojure Script does as well. And Clojure Script is a version of Clojure that targets modern JavaScript engines. So the idea here is, let's take these really fast persistent data structures, and can we do something? How does this help us do UIs? I released a library last December called Ohm, which created a bit of a splash. And basically what we do is we combine the fast immutable data structures that are present in ClojureScript, which again is a version of Clojure that targets JavaScript, and we combined it with React, which is not even a framework. It's more like a rendering library from Facebook. Who here is familiar with React? So not as many people, so we'll dig into React a bit. So Ohm is my attempt to sort of take the lessons that I like from object-oriented frameworks. I actually think things like Next and modern UI frameworks have a lot of lessons to teach us, especially around components and modularity. I also am a huge fan of Mathematica. Mathematica is something that not a lot of people get to play with because the license is so expensive. Who here has played around with Mathematica? Cool. So the cool thing about Mathematica is a symbolic system. It's a very different approach to user interface programming where you can literally have like, I'm going to write a formula. And then there's like a thing called manipulate where you can convert the formula into an object which has handles. And it's really powerful. And I will actually demonstrate something like this later. So taking these two really cool approaches to UI programming and making sure that whatever system we have can accommodate them is definitely a goal of Ohm. As I said, purely functional data structures. So there's like 3 big ideas in Ohm, and this is where we're going to sort of kick it off. So in Ohm, what we'd like to do is we'd like to have data. Imagine that your application, you basically have data, and that's the sort of like database of your application state. We'd like to apply a function and get some virtual version of what we're going to render. And I'll explain why this is useful. Now, say the user changes the data. Now, of course, the data is immutable. It's immutable, right? You can't really change it. So we have some new set of data, D1, which is like, what is the state of the application at time T1? And we're going to apply the function, and we're going to get some new virtual DOM representation. And the reason the virtual DOM representation is useful, and again, this is something that React provides, is that allows us to do a diff, right? We can take the view that was calculated at time 0 and the view that's calculated at time 1, and these are virtual, and we can use React, and React will calculate a diff, and what it will do is it will create the change set that it will apply to the DOM. So the innovation with React is that you don't actually talk to the DOM. But why this is very interesting is what happens if we flip V0 and V1 here, right? We can get the reverse change set, right? The diff will give us the delta to go backwards in time as efficiently as we can move forwards in time. And I'll demonstrate that. So again, why diffs? Maybe you're not convinced, even though the going forwards and backwards in time sounds fascinating. Actually, there are some basic things that are really cool about just doing diffs versus doing observation. If you look at any modern UI framework, regardless of JavaScript, Java, Cocoa, it doesn't matter. They all rely on explicit observation. You have to like observe something. So the nice thing about diffs is that views just re-render when the data changes. There is no explicit observation. I don't have to observe a property, right? If I want to change the UI, React will just calculate the diff and change the DOM. That means I don't have to allocate listeners for when data changes. This actually means there's no resource issues, right? Whenever you imperatively add a listener, you have to remember when that object or that widget disappears or gets removed from the screen to remove the list of listeners, right? So it's a common mistake in JavaScript programs to add a bunch of listeners to the DOM, destroy the DOM, and then not remove those listeners, and those listeners still point to the DOM, and then you have a memory leak. That's like the #1 reason for memory leaks, is that you didn't clean up your event listeners. And again, just removing this means there's you end up writing a lot less logic, right? Code that you don't have to write. Observation code that you don't have to write is just one less bug to think about. So I'll show a quick demo. So here is, I did this post, and this was the post that got people really excited about React as well as Ohm. And people were sort of shocked because the way that Ohm works, for example, if you do a naive backbone to do application, Ohm and React are just way faster. So this is like the flame graph. If this is in Chrome, you can like do a profile, and this looks pretty bad for backbone, and this is actually significantly faster. And this is just due to diffing. And we also use request animation frame. But just to sort of drive the diffing and the going forwards and backwards time thing and drive it home, this is all the code that I had to write to do undo for what I'm about to show you. So I re-implemented to do MVC, which is a very famous reference application for MVC frameworks in JavaScript. So there's only 5 lines of code here that are relevant. Even if you don't read closure script, just note that like if I did this purely in JavaScript, I still would have written only 5 lines of code because of immutable data structures and diffing. So here is to do MVC, and I can go, so this is the same to MVC you might have seen many, many times. Oops. And then I can select this, click this, turn these off, switch tabs. And the 5 lines of code that I showed you is all that I need to add undo. So this is actually going to step through every interaction. And you can see up here that the undo is, this is like, what? This is like 100, I don't know, 200 frames a second. So if you've ever done any object-oriented programming and you've ever had to undo, it's usually a lot more complicated than that, right? So this is the benefit from diffing and representing the entire app state as sort of like a value, instead of having objects have their own state, which is what people are normally doing in object-oriented MVCs. Okay, so if you're coming from the OO perspective, then you're saying, okay, well, so now you have the app state as some big immutable value, and you're able to efficiently update it. But then what happens to modularity? How do components hook into this global state without leaking information to everybody else? Right? That's something you should be concerned about. So objects do teach us this great lesson that you really want these pieces that you can put together. And if you need to pick them apart and reconfigure them, that should not be a sort of like Herculean task. It should be fairly straightforward. That's definitely a lesson from OO that we want to keep. So objects are naturally modular. But I would actually argue, while it's very nice that objects are in a very basic way modular, they're not modular with respect to state. And that might sound confusing, especially if you think, oh, but doesn't encapsulation give you modularity? Doesn't state hiding give you that? And actually, that's almost never the case, and we'll see why. So if we're going to build a new type of system that's functional, we want to preserve modularity, but we also want to achieve modularity with respect to state, which objects fail at doing. So you might be skeptical about this claim. So let's look at a little image here. So imagine you have some root component in your application, and it has 3 subviews, right? And then I read about some component, and it's like, oh, it satisfies the interface that I like, and actually they said that I can swap it in, right? I have this component, and here's some other component that does what the other one did, but something more, right? It extends it. And of course, as the program, like, this is great. I have A, but I actually need B. I'm just going to swap in B. It's just going to work. And you swap in B, and you run your program, and you run some tests, and it doesn't work. And why didn't it work? Right? Because there was hidden state. So if you do any concurrent programming, this is like a classic case of this is thread safety, right? It doesn't matter if you've hidden something at all. Hiding something doesn't matter. Encapsulation doesn't matter, right? It's going to leak out because under concurrency, whether your object is thread safe is really what's important. In the case of Ohm, so imagine I want to do global undo, and somebody hands me widget B, and they hide something. Can I incorporate that into my system that has global undo? No, because there's hidden state inside their thing. So I actually can't integrate it. So this is a way in which objects just aren't modular with respect to state, and encapsulation in the general case isn't going to be enough. It's enough to make you feel like this. And so, having done lots of different systems, you get something, and it has some hidden state, and it's not a fun thing. I could spend more time on this idea, but there's a really great blog post by this guy, David Barber. It's called Local State is Poison. I highly recommend reading it. He covers a lot of things that I agree with. So we're going to stick with this app state idea. The app state, this global app state, is going to be an immutable tree of associative data, and it's global state. And of course, you're like, isn't that a recipe for failure? Isn't like every programming lesson you've ever heard says, global state is horrible. But it's not as scary as it sounds. Almost any non-trivial software engineering system I've ever seen has what? A database. What is a database? A database is global state, right? Every non-trivial application on the web uses global state, right? So there's nothing wrong with global state. It's often what people hate is not the global state. It's not the database, which is the source of truth. What people hate are global bindings, global stateful bindings. So separate the notion of like global variables, which can be rebound, and some oracle of truth that is actually a great software principle and has done a very great job for 50 years. Databases work. They are global state. There's nothing wrong with that. However, in order to build a UI system, we do want to be able to have a local and global point of view if we're going to build modular components. So how are we going to do this? So I'm not going to spend too much time on this, but hopefully if you're of the JavaScript persuasion, this will give you some ideas about how, if you don't want to write ClojureScript, you can take what I'm talking about and implement it purely in JavaScript. It's definitely possible. So a cursor is my solution to this problem. So you have the global application state, and in order so that components don't leak information to each other, there's a thing called a cursor, and what it does is it's a triple. It's basically the value inside the global application state. It's a path to that value, and then it's a reference so that if a widget needs to update the global application state, it can. And if this sounds a little bit dense, I'm going to show some images. So basically, cursors allow us to track the path to some location in the database via normal collection access patterns. Again, this is more, if you're more familiar with functional programming, there's a thing called zippers, which I think are a horrible interface. There's a better thing called lenses, but I didn't really care about some properties of lenses, so I came up with this thing called cursors. So here's an application state. So this is a nested hash map that includes a vector, which is like an array, and then I render some view using this global app state. And so what is some view going to get? Some view is not going to get the original data. It's going to get a cursor onto that data. So here you see that I have the entire app state, and the path that this view is receiving, which is a root component, it's the root of the application, the path is empty, right? We're just taking the entire world right now. And then we have this a state thing so that if somebody needs to update the application state, they can. Now further down here, you notice I'm accessing the foo property inside of that cursor. And then I'm binding that to x. And what I get is a new cursor, which is a slice into the thing, but it also now has tracked the path. How do we get to that piece of data? So if some widget needs to update data, we can combine the path and the state so that we can basically allow widgets to update the database without actually knowing where that data came from, right? It's because under the hood we track the path that components don't need to know where that data actually lives. So we're going to build some other subview, and then we use getIn, which is in ClojureScript. It's just a way to do a nested get. We're going to get whatever's at the key bar, and then whenever we get that, we're going to get whatever's at index 0. So that brings us to the piece of data that was nested inside, which was a map containing a was, right? And the path is now foo bar 0. And again, this just is so that if this other view needs to update the application state, it can take the 3 pieces of data and use that to update that state. But another view doesn't know where that data came from, right? Because again, we're hiding the path. The path is not something that's exposed to the user, right? So this gives us back modularity. Again, I wish I had more time to talk about this, but if you're confused still, go to the Ohm GitHub repo, and there's more details about cursors. But again, the big idea here is to get back modularity. In the end, this is still actually not enough. There are other properties you want from a UI programming system that's functional, and I want to talk about some of those things. So I'm building an application. I've got 3 components, and often what you want to do is you want to customize those components in some way. And this can be something as simple as like I actually need to customize the thing, or I want to create a custom inspector. Like I want to know how long all my components took to render, and I want to do that without changing my own code. Like without having to go write print line statements everywhere, I should be able to instrument my application to determine what's the rendering profile for every component. So this is actually quite difficult to do. Like having done JavaScript, like you end up basically writing print lines everywhere, and it's very ad hoc, and I got sick of that. So I came up with the instrument concept. It's very much an aspect-oriented programming idea. It's a tasteful application of global concerns, and basically allows you to intercept the construction of any component and modify the behavior. And it lets us do generic editors. It lets us do debugging components. It lets us do profilers, what have you. And this might also sound a little bit too abstract, so let's show you a demo. So here is this is actually an Ohm component, and it's composed of 3 subcomponents, which are these radio button text pairs. Down here is the exact same component rendered again. It's actually the exact same thing. The only difference is I've used instrument to intercept those things and then add this UI around them. So they actually are the same. If I click, you notice the bottom guy updates as well. If I click here and I go like that, right? So they're exactly the same. And the reason I was able to do this is because I have this thing called instrument, which again allows me to intercept the widget that I have and then wrap it in some other behavior. I can, like this. That's pretty cool. To show you how much code that involved, it's basically down here. So this is I'm calling the root of my application. That's the regular way. And then here is the way where I was able to instrument my whole application. Notice I didn't have to change anything about my actual application. This is just changing the root component so that every widget gets invoked here, and it says if it's a radio button, build an editor around it. And that's awesome, because again, I don't have to pollute my own application with profiling or debugging or anything like that. Okay. So we saw the demo. And then one other thing I want to show, which I think is important and useful, is so we have this thing called TX listen. So something that also has frustrated me for a long time about doing client-side programming is the question of synchronization. How do I synchronize with the server? And actually, with the prevalence of mobile devices, how do I do offline? Right, offline. And then if I'm offline and the user does a bunch of stuff, when I go back online, how do I synchronize the changes? So often you end up rolling a whole bunch of custom, non-modular, unreusable stuff. And I was like, this is something we can solve hopefully once and for all because we've adopted this functional, immutable approach. So what you don't want to do is you don't want to serialize the entire app state, right? If we're going to sync with the server, or if we're going to write to local storage, you don't want to like serialize everything over and over again at all. So there's a very nice feature inside of Ohm called TX listen, and what it does is it gives you the path. So imagine you have your global app state again. It gives you the path that changed, and it gives you the new and old value. And that's generally a very small piece of information, and that you can write to local storage efficiently or send over the wire efficiently. And again, the only reason we can do this is because there's no such thing as people changing their local state. Like, right, when a widget changes some data, it's changing the data for the entire world, and that's what gives us the path information and the old and new value at that path. And this is just like Git patches. This might sound crazy or esoteric, but it really is the same, right? It's like Ohm gives you a stream of patches which you can efficiently encode, whether you're sending it to the server or whether you're sending it to local storage. Even better, you can serialize to local storage, and when you get back online, you can then pass those on to the server. So things again, it's not like ohm is the final answer, but hopefully you've seen some properties that I think are unique and I think can easily be replicated elsewhere. And it makes some classic hard problems simple and easy. Things like undo and redo and time travel, right? You saw that I was able to do basic undo in 5 lines of code, and I'm going to show a more sophisticated example here in a second. And again, undo and redo and time travel and rolling back, these are generally hard to do in stateful MVC systems. Meta components, things like writing generic debuggers or inspectors or profiling tools, again, generally extremely hard to do. Most frameworks don't make that easy. And in fact, they have to often, if you look at Angular or Ember, they have to spend hundreds of man hours constructing these things for you, right? And if it doesn't do exactly what you want, you're kind of out of luck. Synchronization online, offline, right? This is never fun. And Ohm presents a model where it's at least not terrible. And this is the one thing that if you play around with Ohm, a big goal was that Ohm should play very well with React. So if you actually want to use Ohm from JavaScript, you can. If you get an Ohm component, you can actually use it with React. And then I made it so that basically anyone that uses React, Ohm components work well with. So just to wrap it up, so the idea here is that you've seen some properties, but I want to show some examples of applications. I hate showing my own things. I've shown you a lot of demos that I've done. So fortunately, I can end with some things that other people are building. I think there's a really awesome wide world of the types of UIs you might want to create. One of these is Mathematica. So I have a good friend, Kovas Baguta. He has a really great project called Session, and he's basically building a sort of version of Mathematica that has novel properties yet holds on to the things that are great about Mathematica. So like Mathematica, Session is a symbolic system. It's written entirely in, hopefully, is this going to work? Oh, that might not work. Maybe I have to skip this. Oh, sorry. I'll come back to that. So while we wait for that to boot up, so this is not something that I did. One of the devs from Ableton, like Ableton Live, the music software, last week made this amazing pixel editor called Goya, and it actually, he was inspired. I was hoping somebody would eventually get inspired by my undo example. So he was like, that looks really simple. It can't possibly be that simple. So we built a pixel editor in which he did undo, redo, and then he had a preview based on the time travel, so random access. So you can jump to basically any point in time. So let's look at that right now. So this is the editor. He has some default thing here. This is a Ohm application. So I can draw, this like that. I can switch colors. On the upper right, you should see that we've got different things happening, recording the things that I'm doing, like that, right? So I can click undo, I can click redo, but on top of that, this is actually just random access. Notice the preview at the left. So every image is actually an immutable data structure, right? That's why he literally is recording everything into an immutable value, and then when I jump to it, he's the exact same undo trick that I showed you. He's just setting the state of the application, and everything re-renders, and diffing makes it fast. It's the diffing that makes this efficient. And I can export this as an animation. I've never tried this, but you can click this, and it will put the GIF.js into a web worker and generate the frames from the history. And again, this is hardly any code. Let me just show. So he is Canvas, yeah. So I just want to show his time machine code. is undo manager. So if you've ever looked at undo managers suck. So here he's got 3 lines of code for updating the preview, for showing the preview. He's got undo, some undo logic, push undo the undo stack, undo, redo. What? That's like 50 lines of code, right? That's the entire all the undo capability you see in the project is possible here. This actually also powers the GIF animation. So when he wants to create the animation, he just reads out the history and sends it to a web worker. And I think that's pretty cool. Let's see if session is working. Yes, cool. OK, so this is my friend Kovas Baguta's. This is also an OM application. It's a symbolic computation environment in the same way that Mathematica is. You know, I can like, you know, I can evaluate some expressions here, and look, this is just closure code. If I go like that, so that's pretty cool. It's just like a nice little REPL. Where it gets interesting is that it's symbolic in the way that Mathematica is symbolic. So down here, oops, is that gonna? Sorry. So what I'm demonstrating here is that I have a list, right? This is a list, a closure vector, and it includes an image, like a graphics primitive in there. And I have hash maps, and if I remove this stuff and evaluate that, right? So that's this. It's embedded inside of the list. So in the same way that Mathematica, graphics primitives and numbers and lists and graphs and all these objects are all manipulatable by the user, and they all are the same, Kovas has put that property into this. So if you've seen IPython is like an extremely limited form of this, because IPython it's not really a symbolic system. It is a computational environment, but different types of primitives have different properties, and they don't really work together. And so in this environment, he's tried to make the entire thing symbolic so that if you want to mix and match images and computations and strings, maps, it doesn't matter. It all just works together. And I definitely recommend checking it out. It's very cool. Let me just, I guess I can show one other thing. There's like some graphs, right? It's pretty cool. OK. That was it. That's all I had. Hopefully you enjoyed that, and I'll take some questions.
How does, can I articulate this? You've got a global database with a kind of a facade over it. What does that do to your memory footprint in various scenarios without getting too specific?
So actually, no, it's a great question, and we should get specific. OK, so the question was, it's a great question. So if you're watching this, of course, you probably are like, well, if you did that with copy on write data structures, aren't you going to eat up a lot of memory? I mean, isn't that just going to consume tons and tons of memory? So this is actually a solved problem because we're using structural sharing. So the classic case of structural sharing is a linked list, right? So if lists can share structure. Even if I have multiple lists, if they share the tail, that's memory that's shared between different lists. So we actually use this to implement both random access data structures and our hash maps. So if, for example, if I have each frame of the Goya pixel editor is 4,096 elements in an immutable vector, if I change one pixel, right, just one pixel, I'm going to get a new thing in which the only difference between the old frame and this new frame is one array, right? It's a tree of arrays, and so we only have to change one array, and all the other things in memory get shared. Just to give a more concrete example, somebody recently, or like a few months ago, said, I read your tweet about persistent data structures. I made a game using ClojureScript. I recorded 1,000 frames of the entire game application state. The entire state of the entire game, 1,000 frames. That's 41 seconds of animation. 2 megabytes of memory.
So most things are 0.7.
Inside the data structures, yeah. Yes, this is correct. This is correct. Great question. Thanks. Other?
So for the canvas example, is that actually using React to calculate the difference between the DOM for the
No.
canvas, or is he just?
No, not for the canvas. So that's what's great about the React model is that like he does for the canvas he just renders to canvas. The diffing is really just for the other parts of the UI, and then of course it's immutable when he's updating the pixels. But no, he just calls canvas to render the current state. And that, again, that's exactly how React works, right? How does React work? React creates a change set and mutates the DOM for you. So there's one case where React doesn't can't mutate the canvas. So he wrote his own mutation logic. But again, it's lower in the system, and he doesn't interact with it directly.
But it's not doing like a diff. It's actually just clearing the canvas and repainting that whole frame.
It is. That's totally correct. Yeah, and it's fine to do it that way.
Right. Yeah. I thought maybe somehow it was doing like trying to figure out how it would do the undo of figuring out how to efficiently paint just part of the frame to get back to the previous state.
You could imagine doing more sophisticated tricks, but for this, he just blows away the thing and re-renders it.
Often in an undo scenario, you want to distinguish between an operation that actually changed the state of your data and an operation that just changed the view, so that when you do an undo, like if you had your several tabs that were looking at the data in different ways, if you have an undo chain, you wouldn't want to see changing views as an undo step. You would just want to see, when did I change the data?
Right, so the pixel editor actually demonstrates that. So it doesn't.
I'm more thinking of your first example with the to-do list.
Sure, but the following thing, it's conceptually the following thing. It doesn't record every pixel. So in my undo, it was as if I was recording every pixel modification. And the next one says you don't have to do it that way. You can record an entire change set as one logical point in time that you want to return to, possibly. Is that what you're asking?
Well, my question is, when I implement a change of view by clicking on a tab, say, that is going to update my view state, but I wouldn't want that to be part of my undo state.
Okay, so I didn't cover this. It is possible for various reasons to not encode state changes directly into the application state. So this is actually something we maintain from React. React has a notion of component local state, and that's to encode transient information that isn't something you actually want to record. So there is a way to do this. You can choose what you want to record. That's correct. Any other questions?
So I'm a bit of Thank you. I'm a bit of a neophyte when it comes to all this technology. However, I was wondering about the performance when there's an extremely long stack frame. So if I have several tens of thousands of state and I wish to move forward and backward in that state, am I going to be hitting a very hard performance penalty in rendering?
So fortunately, so the question was, imagine I've decided you want to record 10,000 things, which is pretty wild. You're approaching the type of sophisticated undo that's people do in Photoshop or something, like infinite undo. I can't make any promises because nobody's tried it yet, right? But
For a lot of enterprise applications that are in the web browser, sometimes you could have somebody who sits there for 8 hours doing their job.
Right. So
this massive state.
So to me, it's situations like that. You're going to have to do more design. Do you want to do, for example, exponential decay? Imagine you record everything for the last minute. You record every minute of the hour, and then after that you record every 5 minutes, and after that, it just depends on what strategy makes the most sense for your application, for your user. But I will say that it's definitely the case that React is very fast, so the speed of diffing that's their problem, and it's very efficient. And then again, we've spent now 3 years tuning our data structures for JavaScript engines, and I'm not aware of any pure JavaScript implementations that can compete with the ones that we have. So I would say I would be very surprised if there was a performance problem, And of course, I would love to hear about it if there was. We would want to accommodate that. But I can't say much more than like, depending on what you're building, you might have to like, okay, we're gonna have to cache some of this onto the server, some of this we keep on the client, and again, maybe exponential decay.
So I mean, you support like redo and undo off the end of the stack, but could you be able to just like take an action out of the middle, or would you have to like go undo all the way back to that starting point and then take that one thing out and redo the actions that followed it? Because it might not work, right? I mean, the actions might not play out on that state.
So remember, so Ohm itself doesn't give you out of the box any undo capability. It's just it gives you a model in which it's simple to do it. In the same, like, what does Git do? Git takes, Git is an immutable storage model. Like, it's just the blob. And when you update the file, you're going to record the entire thing over again, and then you calculate deltas. But the beautiful thing is that what is Git? Git is like a snapshotted file system, right? So Ohm gives you a snapshots of the entire application state. It doesn't give you any particular form of undo, but the model makes it simple to create whatever undo system you want. Like if you want merging, if you want branches, all these, like in a regular application, you're like, no way, we're not going to do branching or merging. But in Ohm, it's like, oh, okay, that's going to be like a couple hours of work.
Just an easy question. What's a good place to go, like, learn more about immutable data structures, functional data structures?
So sadly, there's not like a really great resource. There is actually a fairly good write-up by yes. So Hyperion.com has this guy wrote a very good sort of introductory explanation on how they work, and you don't have, it doesn't assume any real knowledge about closure. It's just like what's the algorithm and how it's implemented. I think this in the back. Is this the last one probably?
Can you talk a little bit more about using Ohm as a JavaScript library? I think you had mentioned that it's possible, and any downsides?
I mean, it's only possible in theory. I mean, the main downsides is that it's really not going to be that great. It's definitely optimized to be used from ClojureScript, and it's actually quite large because the way that ClojureScript works is that whenever you write everything in ClojureScript, we can do very powerful, aggressive optimizations over your code. But if you write a bunch of JavaScript code that talks to it, that stuff can't be optimized in the same way. So the downsides is just that it's like you could do it, but you would lose out on a lot of the benefits. So that's why I tried to talk a bit about implementation details, so that if people wanted to implement this purely in JavaScript, persistent data structures. I mean, literally, if you just implement some persistent data structures, most of the benefits you would get immediately just by coupling them with React. All right. I think that's it. Thanks.